Okay, we'll get started in a little bit, 30 seconds or so. Okay, so we'll go ahead and get started. So I believe everyone can hear me. So you should be able to see this slide deck for Monday, September 2nd here. So we're now in Module 2. Everything for Module 1 is now closed, so the train has left the station, as they say. So I hope that, the first 2 weeks gives you an idea of the pace of how this class operates. Again, so Module 2 is going to look pretty much the same format as Module 1. And so what I'd like to do is just go through another brief Canvas tour of Module 2 so that everyone's sort of on the same page where the resources are. And then we'll go through this slide deck and we'll do some problems. So can everyone see the Canvas page now? I think this entire screen is active, so okay. So you clicked on this link to open this page, which has the link to get into the chat meeting today. So again, you need tutorial center information. You can sign up for that page. I definitely encourage you to download the syllabus and read through that. Again, here's all of those different sections. So here's Module 1 that we just went through. Again, all of this stuff is now closed.
You're tracking some though.
So we're in Module 2, which is the structural elucidation using spectroscopy. So let me click in here. This is the synopsis, required reading, chapter learning outcome, and assessments. So this synopsis gives you an idea of what you're going to be learning. The required reading is now chapters 14 and 15. These are the chapter learning outcomes for each chapter. So notice the active verbs: describe, explain, interpret, conclude, interpret, identify, calculate. So those are things you need to be able to do after you learn this material. So our assessments, we have, again, 2 problem sets, homeworks 14 and 15, each worth 10 points. 2 adaptive learning sets, each worth 10 points. You'll have different engagement activities. You'll have an exam. So your course total module, you add all that stuff together, it's about 152 points, and it's about 19% of your grade. So again, there are 5 modules, each about 20% of your total grade. This is the module schedule, subject to change, which it sort of will, because we're going to do mass spec today, because we can get that sort of out of the way before we get into spectroscopy. And I'll explain the difference between spectrometry and spectroscopy. So we're going to learn about mass spec, IR, and NMR. Here's our course schedule. Your homework sets in Orion are due September 25th at 11 a.m. And then your second exam will open on that September 25th at 8 a.m. Again, you have 24 hours to do it. Once you start it, you get 60 minutes to finish it. So let me go back to the module here. So Module 2, I separated out the lecture screencasts. So if you click in here now, these are the material or the videos you should watch. That would be as part of the formal lecture if we were in class. So they're separated: mass spec, IR, and NMR. there will be more added as this module goes on, but these are some to get you started. So the Teams chat recordings for Module 2 will be placed in here. Here's your, if you click here, this brings your link over to, hopefully you can see this. This is the link into Wiley. So there's the online textbook reading you can do. Again, you can click through these either by hitting next or by clicking over to the left side here, depending on the section. So again, chapter 14, chapter 15, readings. The indented things here, there's your homework set 14, Orion 14. Again, you click in here. That's the page, and then click here. It actually launches the link into Wiley Plus where you can do those assignments. So one last thing. It's not posted in here yet, but again, your exam 2 will appear down here as a page. And so let me just click in exam 1. So module 1, here was exam 1. So it says read this first, and I'm not joking when I say that. So you should read all of this stuff before you click this. Don't just go shotgunning into this and take the exam. You should really read all this so you understand what the exam is going to be about. So these instructions will probably remain the same for exam 2. The password might change, but there's the password. A couple people couldn't find it. There it is. So that's, again, module 2. Resources, and then your assessments. So Garima asked, will you be posting answers to the first test questions? No, I will not, for the following reason. You each presumably had a different exam, and you had a different exam because the questions are taken from question pools for each question. So you had, what, 25 questions? So there are 25 question pools. So if question 1 is coming from a pool of 10 different questions, you know, that's 10 possibilities. So I'm not a mathematician, so however many questions per pool, everyone is getting a different exam. So it's impossible to post all those answers. So basically it's you do the exam, you don't get to see it or revisit it again, because again, I'm not making that content. The content is designed in Wiley, and they don't want that stuff posted in Chegg, which people tend to do. So unfortunately, you don't get to revisit it. Any questions on the module 2 layout before we move on? Okay, seeing no questions, hopefully you should see the slide deck again. Here's your molecule of the lecture called Lipitor. So go ahead and get your cell phones out, your tablets out, open up the camera, scan the QR code, and you should see the molecule Lipitor. Okay, so here's some information about Lipitor. So the brand name, I guess, it's Lipitor, and it's sold by Pfizer Pharmaceuticals. So Pfizer is obviously a world renowned pharmaceutical company. It was started by a man, Charles Pfizer, in I believe, Brooklyn, New York. So Lipitor is sold as atorvastatin. So those of you that are interested in medical school or physician's assistant or pharmacy school, a lot of these generic names will sort of end in the same thing. So you see this word statin. So statins are a drug class, and the therapeutic indication is it's an anti-lipidemic. And what does that mean? It basically lowers cholesterol. So this gentleman here, Bruce Roth, led the team of medicinal chemists that discovered this structure that basically lowers bad cholesterol. So here is the bond line formula. So at this point in time, you should know how to interpret a structure like this. So what do these lines mean? What do these letters mean? What is meant by this wedge? So those are things you should know. This is a ball and stick formula of that molecule, so it gives you an indication of basically that the molecule is not flat. So even though we have to draw it flat, it really has a shape. And I think this might be a movie. Can everyone see that movie moving? Okay, so what this is the difference between this molecule here and the one in the movie is that this is called a space filling model. And the space filling model gives you, I would say, a more realistic indication of how this flat structure looks in real life. So as I mentioned at the start of the semester, a skill that you should develop is when you see this flat structure, your mind should really be thinking about something like this. So notice these three benzene rings here, and you can sort of identify them. So see that it's a different color, but the fluorine atom there is green. So see how it sort of resembles like a propeller or a fan shape. And then you have this linear chain here. You sort of see that in this part of the molecule. You see these OH groups, the carboxylic acid. So all these different functional groups give rise to a shape, and the shape of that molecule targets a receptor that lowers or basically prevents cholesterol from building up.
Thank you.
There's the pill itself. So Lipitor, it's sold in 40 milligrams. So again, those of you that are aiming to be physicians or those of you that want to be pharmacists, 40 milligrams is not a bad dose if you have to take it once a day. The lower the milligrams, the better, obviously, because as you see over the course of these 2 semesters, it probably takes 8 to 12 chemical steps to make this. So the lower the dose for the patient, the more material or the amount of material that the company can produce. So if the patient had to take 400 milligrams of this, obviously the company has to produce a lot more, and that's really not economically efficient. So let's do some questions. So in the chat, you can put your answer. So learn, explain, apply, predict. So that's an abbreviation for LEAP. We all want to leap forward in our knowledge. So in the anti-lipidemic medication Lipitor, how many sp2 hybridized carbons do you count? So you can type a letter corresponding to the answer or your number. So I'm inclined to say the best answer is 24. So where do we see them? This benzene ring has 6. This benzene ring has another 6, so that's 12. A third benzene ring, so that's 18, 19, 20, 21, 22, 23, and 24. So maybe you can, in the chat, you can type a couple words here. What is the expected geometry for an sp2 hybridized carbon? Again, sp2 hybridized carbon has what sort of geometry? Trigonal planar. And so in your mind, when you make these connections, trigonal planar. So as we saw in the movie, that part of the molecule, trigonal planar, a benzene ring is like flat. So let me go back. You see these little white spheres in the benzene ring, they lie in the plane of the carbon atoms. So the benzene rings themselves are flat, you know, when you're looking edge on. So the geometry gives rise to the shape of the molecule. So the next one, what about sp3 hybridized carbon? How many sp3 hybridized carbon do you see? Rosemary's jumping the gun. I appreciate that. That would have been my next question. What's the total number of sp3 hybridized carbon, though? So even though, you know, someone might throw a response out pretty quick, I still encourage you all to do the question yourself and put your own response in the chat. Because at the end of the day, you know, your response is just as valuable whether it's right or wrong, showing that you put some effort in towards the participation. So I count 9. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, part of the reason why I'm asking you to do this stuff, and it may seem pretty straightforward now, but again, it should be, as you do more of these, it should be like your mental muscle memory. So Rosemary's asking about NH, and basically I'm asking about carbon only. So see carbon, I'm not asking about the heteroatoms. So we're not considering nitrogen in that question. So what you just did is you counted the sp2 hybridized carbons, you counted the sp3 hybridized carbons. And so again, this is all building up, we're scaffolding, we're moving up Bloom's taxonomy. And so the reason I'm asking you to do that is because when we start looking at nuclear magnetic resonance spectroscopy, we're going to figure out, looking at that piece of data, where those different hybridized carbons appear. Because when Pfizer Pharmaceuticals sells this pill to a patient and they take it, they basically had to prove that this structure is what is in that pill. And so we're learning the thought process of how to elucidate structure. And what that means is this is a structure on a piece of paper. We're going to look at data and make assignments. So this carbon right here, that goes to a certain peak. it's different from this carbon, right? This is sp3 hybridized. This has 2 hydrogens. This is sp2 hybridized. It has no hydrogens. So on a spectrum, those 2 carbons should appear at different regions. So that's what we're doing. We're just learning the fundamentals of that now. Okay, so how many pi bonds are present in Lipitor? Pi bonds, double bonds. So yeah, the consensus seems to be 13. And so let's count those. This benzene ring has 3. Another benzene ring has 3. That's 6. Another benzene ring, that's 9. Another ring has 10, 11. Then we have 12, 13. So we have 11 carbon-carbon pi bonds and 2 carbon-oxygen pi bonds. So just by doing that exercise, we've differentiated the pi bonds. And so what you'll notice is that even though these 3, 6, 9 pi bonds occur in benzene rings, notice what each of them is bonded to. This is bonded to nitrogen. This is bonded to a carbon. And then this is bonded to a carbon. So those rings are in different environments. Look at this pi bond. What is this carbon oxygen? What functional group is that a part of? Maybe in the chat box you can write your answer. So that's part of an amide. Then what about this carbon oxygen pi bond? What's that part of? So Carly wrote alcohol, but again, we have to consider that the OH is bonded to this CO pi bond, so that is a carboxylic acid. So even though you have 2 CO pi bonds, they are in different functional groups. So this carbon here and that carbon there, acid versus amide, we will resolve them using carbon NMR. They will occur at different chemical shifts. So we can know, okay, it's in this region, it has to be an acid. It's in this region, it has to be an amide. So what am I getting at here? You are observing with your eyeballs this structure on the screen. So we can sort of do these exercises. But what if you were given a substance, a white powder, and then you were given pieces of data, and you had to look at the data, put it all together, and elucidate, that's what that word means, elucidate the structure. That's a much more complicated process, but really that's what this dude right here, Matt Donahue, is the instructor of this course. I want to show you how to think like that because it moves beyond memorization. It starts making different connections with all these concepts we're going through. So Katie had a question. It doesn't relate to this particular molecule, but a triple bond does have 2 pi bonds. That is correct. So a triple bond, as we've seen, can be in an alkyne. That's a carbon-carbon triple bond, or it can be a carbon-nitrogen triple bond. That's a different functional group called a nitrile. Any questions before we move on to our next slide? So this slide is as I mentioned, we're going to do the mass spec part of chapter 14 first, because I think it transitions easier into the prior exercises we've done. So consider this molecule we've seen before, ethynyl estradiol. Maybe in the chat box you can write the molecular formula, and then from the molecular formula you can calculate the molecular weight. So with the molecular formula, you're going to count the total number of carbons, the total number of hydrogens, and the total number of oxygens. So you should write something like CXHYOZ, or X, Y, and Z are the counts for each of those type of element. Any responses yet? C20 is correct. Putting some thumbs up. Ooh, sorry, I gotta take that one back. So Rosemary, Aiden, Carly are correct. Ian is 2 hydrogens off. So yeah, it's C20H24O2. That's the molecular formula that I got. So from that, what is the molecular weight? You remember how to do that? So I'm getting more 296s in the chat. Rosemary threw out a 294. I think she was just a smidge off on the hydrogen count, perhaps. So it's 296. So again, what did you do? C equals 20 times 12. That equals 240. H equals 24 times 1, that equals 24. O equals what, 2 times 16 equals 32. So there's the numbers we use to get 296. So in essence, everything that you just did was the concept behind mass spectrometry. Mass spectrometry is simply an instrument that will tell you the mass of a substance. So it's where you get the data. So you've done this by visual inspection. The mass spectrometer just gives you the data. So can I point out the carbons? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So here is a piece of data from a mass spectrometer. So let's point out the hydrogens. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So again, you looked at this, you counted carbon, you counted hydrogen, you counted oxygen, you multiplied the atomic mass by the number to get 296. This piece of data here is a mass spectrum. So let's point out, so we're situated, we understand what we're communicating when we interpret this. The x-axis is called mass over charge, m over z. Z is defined as charge. M over z. For us right now, z is equal to 1, so you can just think of this axis as mass. Relative intensity, that usually, even though this scale goes to 120, relative intensity, you can think about abundance. It's basically 0 to 100. So Sarah's asking about carbon-carbon triple bonds. So yes, a carbon-carbon triple bond alkyne has to have 1, 2 carbons. This is a carbon, that's a carbon. Okay, so x-axis is the mass. The y-axis is the intensity or abundance. So you calculated 296. I know it may be hard to see on your screen, but this peak right here at the highest mass is 296, which corresponds to what we calculated. The mass of the parent, or excuse me, the mass of the intact molecular formula is called the parent. So the parent ion at 296 corresponds to the molecular formula. So you see that number, this peak here, or signal at 296, that's what we calculated. That includes every atom of the intact molecular formula. So what about all these other red lines, these signals we see in this mass spectrum? Anything at a lower mass than what you calculate for the intact molecular formula is called a daughter ion. So here's the parent ion. Again, that's the entire intact molecular formula. Anything lower, you're losing mass through a process called fragmentation to form a daughter. So there's the parent, there's the daughter. Notice that this peak here, which corresponds to 100% abundance, that's called the base peak. So the parent is the intact molecular formula. The base peak is the 100% abundant peak. So notice that the base peak is at a mass of 213. So let me get out my calculator because I suck at doing math in my head. If I take 296 and I subtract 213, so 296 minus 213, that equals 83. Thanks, Ian. It's quick on the draw there. That's 83. So the difference between 296, 213 is 83 mass units. So what is happening in this instrument, as this sample is injected, it is losing a fragment of mass corresponding to 83 mass units. So somewhere along this thing, it's losing a certain number of carbons, hydrogens, or oxygens that corresponds to 83. And so it's forming a base peak at 213. And again, I'll repeat this a couple times. We'll go through it. So what I want to point out to you is that look at sort of how this data looks. Again, the red lines are data. Each molecule has a specific sort of fingerprint, maybe that's a way to describe this, of how this mass spec data looks. So it's fragmenting, you get this base peak, then you get these clusters. See this cluster here? This is a cluster, this is a cluster. So it's sort of like a fingerprint for that molecule. And if you're interested in like forensic toxicology, mass spectrometry is very important for that purpose because it allows substances to be identified in a very specific fashion. So a little bit more on the theory here. Mass spectrometry deals with atomic masses, and if you remember, elements can have isotopes, so we have to consider the isotopic masses of those atoms and their natural abundances. So I'll create a screencast for this that you can watch at a later date in a little bit more in depth. But basically, here's the atomic number. In this first column, there's the name. So atomic number 1 is hydrogen. There's the symbol. And this is the mass of a hydrogen atom. So for the most part, what we've been doing is just calling it 1. But notice for a mass spectrometer, we're now going out 1, 2, 3, 4, 5, 6 places past the decimal. And so this abundance is telling you for the hydrogen atom, just H, it is 99.9885% abundant on Earth. The hydrogen, the next isotope of hydrogen is called deuterium. So it either has the symbol 2H or D, and notice its mass goes up by 1. So its abundance is basically, when you're calculating this abundance, it basically has to equal 100, right? So this is lower abundance. It's 0.115%. Tritium is the radioactive isotope. Its mass is now 3.016049. And its abundance, its trace abundance. Basically, we humans produce it. It's not really something you can isolate by extracting it from a rock or something. Carbon has 3 isotopes, C12, C13, and C14. C12 is the naturally abundant isotope at 98.93%. C13 is a stable isotope. It has 1.07% abundance. And then C14 is the radioactive isotope, and there's its mass. Nitrogen has 2 isotopes, N14 and 15. Oxygen has 3 isotopes. So notice that the stable isotopes are the highly abundant ones. Fluorine, chlorine, bromine, iodine, these are going to be very important for us because they have specific signatures in the mass spec. So that when we look at a piece of mass spec data and we see that signature, we can say, okay, it has this halogen in it. Fluorine has only 1 isotope. Chlorine has 2, 35 and 37. Look at their abundance. Look at these two numbers, 75, 24. So we'll just say 75, 25. If you take 75 divided by 25. I know this is simple math, but what is that ratio? This to that, what's the ratio? Just type in some numbers in the chat box. It's 3 to 1. So I'm going to show you this visually, but I'm just going to explain it now. If you have a piece of data and the parent ion shows a peak with a ratio of 3 to 1 at the parent region, you should know, okay, by this table, that molecular formula has chlorine. So let's look at bromine, 7981. What is this ratio here? So it's 1 to 1. So again, if you look at the parent ion and you see two peaks in a 1 to 1 ratio, you can say I'm reasonably certain that has bromine in the molecular formula. Iodine is a single isotope. It's 100% abundant. Again, I will explain this table again in a screencast of how we actually use it. But in the interest of time, so we can get on to doing some problems, I just want to move on to the next slide. And so the data that I'm going to show you in the subsequent slides is taken from the National Institute of Standards and Technology, or NIST. So the webbook.nist.gov. And NIST falls under the United States Department of Commerce. So I'm sure we're all aware there's a presidential election coming up. So the people that run these departments, they're actually political appointees of the president. So the people that run these sort of institutes, in my estimation, they're probably not political appointees. They're probably lifelong scientists that sort of ascend to directing those institutes. But it is interesting. There's the, if you know about Dr. Fauci, through the National Institute of Allergy and Infectious Diseases. So he's been put through the ringer based on his scientific views, not jiving with basically what political appointees want him to say. But anyway, the NIST, you can find data for pretty much everything. So this is where I got this data here. This mass spec data comes from NIST. So this slide is called Chemical Forensics, Molecular Fingerprinting, and Mass Spectrometry. So look at these structures. All three of these structures are steroids. And you might think, well, steroids, basically you shoot them and you get big muscles, but there's a lot of different steroids in your body. And a steroid is a hormone that signals to your body to some biological process should occur. So here's testosterone. This is an anabolic androgenic steroid. This molecule, gestrinone, treats or causes endometriosis. And here we have tetrahydrogestrinone. This is a synthetic anabolic steroid. So I have this picture here of Icarus. This is a movie on Netflix about, or a documentary about steroid use that the Russians were using for the Olympics. And so why do I say chemical forensics? And so this is the fingerprint of testosterone. So I know I don't have a stack plot, but this does look different from the ethinyl estradiol. So the reason why athletes have to give urine samples is that the urine is then injected onto a mass spectrometer, and they can see if there's above normal levels of testosterone. And so synthetic testosterone will look different from testosterone that your body produces. So that's how people get caught doping. So when athletes dope, they're injecting or ingesting synthetic performance-enhancing drugs. In mass spectrometry is the instrument they use to find that. So any questions before we get to some problems here? So let's click on this slide. So notice on this slide, there is no chemical structure. So what you are doing now is you're taking data and you are elucidating or proposing a structure. And this is what I find enjoyable about organic chemistry, is that you really have to put together all the concepts you've learned to really figure things out. And that's what we want to do, is be able to think and figure things out. So it says putting it all together. Determination of possible isomers from mass spectral data. Okay, so you are given a mass of a parent ion that's 58. So you're given the molecular weight essentially is 58. We see that here. That's the parent ion right there. Determine the possible isomers for only carbon and hydrogen containing compounds. How can you use unique carbon and hydrogen to differentiate the isomers? Here's a second problem. Can you figure out what the structure of the M over Z 43 fragment is? So this would be the base peak. Hint, what does 58 minus 43 equal? So let's focus on this first part of the question here. So you're given two clues. The molecular weight is 58, and it only consists of carbon and hydrogen. So how should you approach this? The first thing you want to do is figure out the molecular formula. From the molecular formula, determine the degrees of unsaturation, and then from there you can start connecting the carbons to carbons, carbons to hydrogens, and proposing structures. The second prompt is what you use to differentiate those structures. So let me sort of walk you through. Let me propose a question before I write something down on the .cam, which I'm going to switch to now. So molecular weight is equal to 58. And so again, we got that from the parent mass. M to Z equals 58. Let me ask you a question. What is the maximum number of carbons you can have? Can you hear me now? All right, sorry about that. So Hannah threw out 12 times 4 is 48. So 4 is definitely the correct answer. So one thing you want to start with when you're given this sort of problem is all we're doing is we're taking that parent ion and we're dividing by the atomic mass of carbon, which is 12. That gets us this number. Notice that number is not exactly 4. So in essence, you always want to round down. So we want to go just to 4. So I'm going to show you the reason why. As Hannah pointed out, 12 times 4 is equal to 48. And what is that? That is the carbon contribution to the molecular formula. So we said as a clue, there's only carbon and hydrogen, right? So we can then say the max hydrogens is equal to 58 minus 48. So that gets 10, right? So what did we just do? H is equal to 10. We have C4H10. That is what we are proposing. And so we're proposing that. It's a claim. So why couldn't we have 5 carbon atoms? What's the issue with 5 carbon atoms? So Columbia says it goes over the molecular weight. Yeah, exactly. So all we're doing, we're just using logic. We're just thoughtfully thinking about these things so that it makes sense and it fits, and we're not violating any of the data that we've been given. So C5 equals too much. So that gets us what? 60? That would get us an M to Z equal to 60. And so that's greater than 58. Why could you not go to C3? What's wrong with C3? So 3 times 12 is equal to 36. 58 minus 36 is equal to what? 46, 56, 22. C3H22. That's crazy, right? That's way too many hydrogens. So here's our Goldilocks scenario. That's just right. The porridge is just right for eating. C4H10. And let's just verify that. C4H10. How many degrees of unsaturation are in C4H10? So yeah, there's 0 because we know CnH2n plus 2, where n equals 4. That should be C4H2 times 4 plus 2. So we see that they're pretty much the same, so there's no degrees of unsaturation. Again, think about what that means. There's no pi bonds, there's no rings. So why don't you take a couple minutes and for this molecular formula, propose some isomers. You can either write those isomer names in the chat or you can show your camera with the actual structures. And so what that is going to do is get to the second part of the question here. How can you use unique carbon and hydrogen to differentiate the isomers? So Hannah, you have one of them there. That looks good. Can you think of another one?
Oh, can you see 3 of them? I thought I do 3.
Oh, sorry. I was only seeing one. The 2 you have stacked are correct. Aiden's, yours look correct. So the other one you have is actually the same compound as the top one.
Yeah, I was wondering about that one. That was like my question one that I didn't know. It was like.
So those are the same.
Okay.
Columbia, you have 2 of them correct. One of them is not correct because you have a ring, and a ring is a degree of unsaturation, so you can't propose that. Ian, I only see one. Can you move your, okay, I see both. Ian, you have both correct now. Carly, your third one is the same as your second one. You've just sort of drawn it in a different way, but 2 of those are the same. James, yours are correct. Jalen, yours are correct. So now think about of the ones you've drawn, how many unique carbons does each have? How many unique hydrogens, and what are the ratio of the hydrogens? How do you differentiate those 2 isomers? So let me type the names in the chat first. Oop. Sorry, butane. So for those of you that didn't quite get it yet, butane and 2-methylpropane. Maybe you can convert those names into structures before I show you on the document camera. So how I like to do this when I'm proposing these, we know there's 0 degrees of unsaturation. So I'm going to put a 4 here, and that 4 corresponds to, here I'm going to draw the linear carbon chain. 1, 2, 3, 4. Right there. That's the first one. I've accounted for all 4 carbons and all 10 hydrogens. This is butane. There's no other isomers I can draw with a C4 linear chain because I've used all the carbons. So now what I'm going to do is I'm going to knock it down 1. I'm going to go to a C3 chain. So now the longest chain I'm going to draw here is 3. 1, 2, 3. So I have 1 more carbon to put in there, right? If I put it at 1 or 3, I'm just making butane again, so I'm not allowed to do that. So the last carbon I put on position 2, and this is 2-methylpropane. So how many unique type of carbon does butane have? So it has 2. How many unique type of carbon does 2-methylpropane have? So 2-methylpropane, how many unique type of carbon? I see some 3s popping up. It's actually not 3, it's 2. This, and that are all the same. That's 1. And then this is different, so that's 2. So how many unique type of hydrogen does butane have? So Aiden has some answers in the chat box, but let's go ahead and do this stepwise. So this has two type of hydrogen as well. The methyl groups are the same. The methylenes are the same. So that's our 2. Then what is the ratio? So for these two unique sets, so we said 1 is equal to 4, 2 is equal to 3. What's the total count of hydrogens for 1 and 4? So Sarah has it 6 to 4, and again, that gets us 10. The total methylene count, 2 and 2, that's your 4. So let's do the same exercise for 2-methylpropane. I know we're going to go a little bit over, but if you just bear with me, I'd like to finish this slide before we adjourn. So the total, how many unique sets of hydrogen do you see? So there's 2, right? You have methyl, 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 and then methine. So what are the ratios for those then? So 9 to 1, 3, 6, 9, and then 1. So what I'd like to point out to you, conceptually, this is what proton NMR is. These ratios, see how 2 and 2, 2 and 2 are the same? These ratios is what we will use to differentiate these isomers experimentally. Now let me ask you, again, I know we're going to go a little bit over, but maybe I could have a couple more minutes. If you refer back to the slide that's up, in this last prompt here, it says, can you figure out what the structure is of the data presented of the the mass over charge 43 fragment? Hint, what is 58 minus 43 equal to? So in the chat box, what's 58 minus 43? It's 15. So let me point out that the red line that you see on this spectrum, that is like the explicit data. You see a number 43. 58 minus 43 is 15. That is a fragment that the parent loses. So as Tenley pointed out, that was going to be my next question. And Max asking, does that mean it's a methyl group? Yeah, so you are losing the mass of a methyl group. 58 minus 15 is loss of a methyl, so you see a peak show up at 43. So if you look at these two structures, you see that this linear one, that has 1, 2 methyl groups. The branched one has 1, 2, 3. So I'm inclined to say that the data that you are looking at belongs to this structure, because if you think about it, you can lose a methyl group here. So if we lose this methyl group, or you could lose it here, or you could lose it there. So this structure is more apt to lose a fragment corresponding to 15 or a methyl group just because there's 3, whereas this one has 2. So there's a methyl you could lose, or there's 1. So I know that might have been a little bit rushed at the end there, but really what we've conceptually looked at is carbon, proton NMR, and then mass spec data to synthesize the structures given just simply starting with, look at what we did. We just started with that 58, and we proposed 2 things, and we were able to use some thought process to differentiate. So Mac is asking, does the height mean anything? So the height does mean something, because that peak at 43, so what does it mean? If we consider 2-methylpropane and we lose a methyl group. So this is 58. The peak that you see is 43. The peak that is lost is 15. So we're probably seeing something like this. So that's telling you it's 100% abundant, meaning it forms the most when you run the experiment. So again, we'll do some more of these in the next chat, as well as getting into the infrared spectroscopy. Carly's asking, the ratio thing for unique hydrogens always has me confused. So let me flip this over and sort of go through that again so we can leave all on the same page. So we said that there's two unique sets of hydrogen because the 1 and 4 are equal, the 2 and 3 are equal. And so what we're doing in terms of the ratio is we're simply counting. Carbon 1 has 3 hydrogens, carbon 4 has 3, so 3 plus 3 is 6. Methylene, methylene, so 2 plus 2, that's 4. Now for this one, the methyl groups are all the same. So 3, 6, 9. And then we have a methine as 1. So notice in both cases, they both equal 10. So Carly, I hope that answered your question. If not, we can schedule a meeting to go through that. But basically, I'm going to adjourn this chat session. We'll do some more of these type of problems in the next chat session. So this one actually is going to contain oxygen. The next one has nitrogen. So we'll do some more of the same stuff. And we'll take mass spec data and propose a structure. So please go ahead and start looking at your readings in your homeworks and look at some of the screencasts that are posted. And then we'll meet again on Friday for a chat. So in the meantime, if you need help, shoot me an email and we can resolve your issues.